first results and opportunities for round 3. So, Aurelio, your floor.
Yeah, good morning. I guess we need to, how do we project the slides?
I think it's a good idea if you...
No, it's okay now.
Okay.
All right. Good morning, everybody. Thank you for being on time. And for this first talk, it's a pleasure to be here. And I've been charged with telling you about the latest developments on the LAC front, in particular in the context of round 3, current results and opportunities. And early in the morning, perhaps it's good to remind ourselves why we are here. I mean, we're interested in answering big questions, like, for instance, why the Higgs boson is so light, or the origin of matter-antimatter symmetry. Of course, there are questions that are too hard. We're not going to be trying to tackle here. But for the ones we can address, we can use the LHC. I mean, this is currently, we think, our best shot at addressing them in the near future. There might be more opportunities in the further on, but this is our machine. And we have a lot to do with it in terms of direct searches for new physics and precision measurements. Okay, so let me welcome first, early round 3, 2 new experiments joining the family at LHC. As you may know, we have now PHASER and S&D at LHC starting this year. We are excited to learn about the upcoming results in the near future. For this talk, I was asked to tell you about the latest developments from ALAS, CMS, and LHCb. Unfortunately, I will not be covering ALICE, but I'm hoping we're going to be learning more about the progress there in upcoming meetings. All right, a few reminders about the LHC timeline for those of you who have not followed closely. Just 5 years ago or so, we ended run 2. Collected lots of luminosity at 13 TeV, proton-proton collisions. And just July this year, a decade after discovering the Higgs boson, we started run 3 at a slightly increased center of mass energy, 13.6 TeV, with improved detectors after the phase 1 upgrades. Now, further later on, we're going to have the high luminosity LHC starting in 2029 with round 4 and going on for a while. But therefore, we need major detector upgrades to really cope with instantaneous luminosity. So really, pile-up is a driving force for us at the LHC, and it's been growing over time. And this is, of course, a deciding point for us to keep improving our detectors. Moving from run 2 to run 3, we are about increasing a factor of 2 in pile-up. So we had to have some upgrades there. But then we are going to have at least a factor of 3 into the high luminosity. That represents a technical challenge, but Spanish groups are making big contributions there. Okay, before we talk about run 3, let me just briefly flash some of the run 2 legacy. We're going to learn, we learned about it in the past CPAN meeting, and we're going to learn a bit more later today. But just to remind you, we are moving into run 2, but we are not done. Into run 3, we are not done with run 2. The analysis is still in flux. We have fantastic results that have been achieved over the last years. Both ALAS and CMS reached more than a year ago the milestone of 1,000 papers published and covering an extremely interesting and broad program. And for more details here, I'm going to just flash a few results. For more details, or rather the scope of it, I refer you to Isabel's talk at the last CPAN meeting, which was quite nice, giving the highlights from run 2. But just to remind you, we are thoroughly investigating the standard model. In the Higgs sector, we made a lot of progress. Javier will tell us a bit later in the morning about it. On top physics, we are measuring the top mass to an incredible precision and probing top production processes over many orders of magnitude, going into the rarer and rarer. On QCD and electroweak, we're measuring parameters of these sectors with incredible precision into the multi-TeV regime. As we learned yesterday, the W mass is a point of attention. It is a reminder that the precision measurements are key players of our quest, for understanding what's going on. But also measuring production cross-sections all over the place, from the highest cross-sections in die-jet production to incredible precision compared to theory to the smallest cross-section in multi-boson production on the electroweak sector. On the flavor sector, we are scrutinizing CP violation and mixing in great detail. we are back to the 50s on spectroscopy, discovering more and more hadrons, as time goes by, and including tetraquarks and pentaquark states, and probing also rare decays that we think would be a good shot at understanding what's going on at a deep level and finding surprises. I mean, the so-called B anomalies. There are many of these absorbables that have been showing discrepancies and that seem to be growing. Sometimes they're not, they're moving back to standard model, perhaps. But it's an area of research that is drawing a lot of attention, and we are hoping this could perhaps signal the beginning of a new revolution in fundamental physics if it turns out to be true. And in the meantime, while doing all these measurements, we are searching everywhere. We are really putting under serious pressure, the naturalness idea in supersymmetry. We are searching for beyond standard model processes, from very low mass particles up to the highest masses, in a wide range of final state signatures. Looking, for in the lifetime frontier across orders of magnitude in lifetime for new particles to be produced, and even in the limit of fully stable invisible particles, probing for dark matter in complementary ways to direct detection experiments, or even understanding to what extent the Higgs boson may be a portal to the dark sector. Okay, so we've been busy, and it's been quite productive so far. And of course, this is a good starting point for now. With all this experience gained, move into round 3 with new ideas and new energy to keep going on. All right, so before we start round 3, of course, as I mentioned, we need to upgrade our detectors. I'm going to tell you more about it in a bit, but this is what we spent some years early, before the start of round 3 during the LS2 in particular, upgrading LR-CMS LCB analysis, but I will not discuss about it today. Okay, here we are, the beginning of round 3, with this slight increase in center of mass energy. Seems like not much. It doesn't help for the production, a lot for the production of the lightest particles in the standard model. But you can get factors of 2 gain in cross section if we are talking about still that PDF slight gain pans out when it comes to very heavy particles. So this is going to be interesting in that respect. We are luminosity-wise, Atlas and CMS will be dealing with about the same instantaneous luminosities as at the end of round 2, but LHCb will experience a factor of 5 increase in instantaneous luminosity. So PyLab will go up by a factor of 5 to 5 interactions per crossing. And Atlas and CMS, as I told you, will be about 60. And integrated luminosity-wise, just round 3, we expect a significant jump with respect to round 2, and a factor of 2. Atlas and CMS, we expect to have delivered about 250 inverse femtobarn and LHCb 15 that already will allow us to do quite a bit, as I will discuss later. Okay, just a brief summary of what's been going on during the year. After the end of long shutdown, throughout April and June, the LHC machine was commissioning, and there were beam splashes throughout spring that allowed the experiments to commission their subdetectors and exercise combined data taking. As we know, the run started on July 5th, celebrating the 10th anniversary of the discovery with the first stable beam at 13.6 TeV. And then this was, of course, greatly celebrated by collaborations. We produce all these beautiful event displays that we can enjoy. Then during summer, where intensity was further ramped up, August became a production month for proton-proton collisions till the end of August, where unfortunately there was this RF cryo incident that led to a 1-month downtime. Nevertheless, LHC started strong again in end of September with the longest ever field for LHC forward, special run, more than 2 days, and then October again, just field after field, producing luminosity like crazy. It's been extremely productive. It's been going on throughout November, where we even found time to do a Vandermeer scan to measure luminosity accurately, and even have an opportunity for me to show you first event displays on first lead collisions from ALICE, as well as ALAS and CMS. So it's been a lot. Okay, this is ending. The run is ending next Monday, November 28th. But during the last week, namely this week, LHC has pushed even further and tried to test the limits of the machine, increase the high intensity to highest intensity and instantaneous luminosity, just during 2 fields, just to see how the machine is behaving where we are going to be next year. And it has worked quite well. Okay, so all in all, the performance has been exceptional. You can hardly imagine a better storm. All the goals for 2022 have been reached or surpassed in terms of beam intensity, peak luminosity. Even the integrated luminosity, we are anticipating 25 inverse femtobarns for all and CMS. As on November 22nd, we are at 38 inverse femtobarn with 1 more week to be added. LSCB about 1 inverse femtobarn. And many records broken, in terms of course, last week, the instantaneous luminosity, 2.5 10 to the 34 with more than 73 pile-up events per crossing. And even, just a day means 1 inverse femtobarn. This is, incredible, right? So this is very nice. And okay, let me tell you how the experiments have been doing throughout this time. Now, as I mentioned, the detectors have been upgraded, and upgrade in the case of LECB is a misnomer. It's just a new detector, okay? The less than 10% of the channels have been kept, 100% of the electronics replaced, new DAQ and a data center. And here I will just give you some flavor for some of these developments. And I refer you to Paula's talk on the Rail LEC parallel session for more details. But okay, starting with the pixel detector, this is the heart of LCB in many respects. There is a new detector, the Velo, which is 41 million pixels of 55 microns by 55 microns, just closer to the beam, 3.5 millimeters from the beam, which should allow for much improved primary vertex and impact parameter resolution. This was completed in May 2022, and the commissioning has been going very well with tracks and vertices reconstructed, alignment in place. So this is ready to go. After the Velo, we have the tracker. Just before the magnet, there is the upstream tracker is still being put in place. This is a new high granularity silicon microstrip tracker that wasn't there before. About half of it has been instrumented, and the plan is to finalize it during this year's technical stop. But we do have the scintillating fiber tracker, which is now has high granularity, and this has been exercised already in combined tracking with the Velo. And here you can see, for instance, plots about the improved track chi-square, for this combined fit as you have the various sub-detectors aligned. Or first invariant mass distribution for the cascade minors, that are decays that are happening inside the Velo and reconstructed by both detectors. Then there has been also updates to the RIDGE with improved optical systems and better photon yield and resolution. There's going to be a busy environment for this detector, but we expect that these developments will allow to maintain particle ID performance at increased luminosity. And this detector is ready, and probably this may be obsolete. It's already being used in runs with track reconstruction. And then there is the calorimeter. There are more updates, but I just mentioned a few. Here, these detectors have been in place for a while, and it was already going on in data tech in spring. There's been upgraded front-end electronics, and the scintillating pulse detectors and pre-shower in front of ICA were removed. But this detector now allows for the first time electron and photon separation at the high-level trigger. And even just with a coarse energy calibration of the readout with a LED, you could already find a nice pi zero peak, which you can in turn use to further calibrate the energy response of the detector channel by channel. And then one of the big developments at the LCB is just going ambitious here is moving to a software-only trigger, which can operate at 30 megahertz processing rate and do basically partial event event selection and full reconstruction at 1 megahertz rate through a combination of GPUs and CPUs. And this gives you the highest throughput of any HYPE experiment currently, and removes a bottleneck that this experiment had in the past. Now the yields are increased, hadronic yields are increased by a factor of 10, through this development. And well, everything seems to be working very well. We have this trigger system operating basically at almost at the nominal rates in terms of input and output with all sub-detectors except for the upstream tracker included. And okay, I mean, this is, seems to be an idea that is just working. Okay, let me tell you about Atlas. Of course, Atlas now is just not such a substantial upgrade, of course, as LECB. The real upgrade will happen in time for round 4. But nevertheless, there's been a number of developments in various detectors that triggers that are important. I will mention some details. One of the most important ones is the new muon small wheel detector, which is covering this eta range, and is replacing the previous NCAP cathode strip chamber-based detector with now a thin strip TGC and macromegas detector that allows for a better trigger rate capability. The integration is well in place. You can see hits in the detector, in collision events, and currently it's being commissioned. Or the muon triggers related to this detector are being commissioned and integrated into the level 1 topological trigger, which is very important for the B-physics program. There's been quite a few upgrades on the level 1 trigger system. In particular, liquid argon has a factor of 4 improved granularity in 2 of the layers. These inputs that digital now are fed into level 1 calorimeter trigger that has new boards that allow better discrimination of electron, photons, jets, and taus, and with improved turn-on curves and reduced rates. Level 1 muon trigger is capitalizing on the new small wheel now to have much reduced rates of fake muons. And we have higher granularity in PT that allows for better mass resolution useful for B-physics. And then all these inputs are fed into a level 1 topological trigger with a new board that can make sophisticated topological event decisions at the level 1. This is then being followed by a number of developments on the high-level trigger. In particular, the software has been fully redesigned to be multi-threaded compliant. We are capitalizing on many developments I have taken on the offline world. In particular, tracking has been sped up by a factor of 3. Now we are able to run at the HLT level, full scan tracking on hadronic signatures, and even large radius tracking for displaced ones, and it all fits the budget. And we have the trigger now strengthened with all the latest offline-like reconstructions. We have particle flows, we have graph neural networks for bit tagging. The most sophisticated performance is part of the trigger decision now. The trigger is, of course, operating for the mainstream at the order 1 kilohertz output rate, and this is immediately reconstructed in the tier 0. But we have also other streams to strengthen the physics program. I mean, we have a delay stream of events that we would like to just trigger at a higher rate for maximum efficiency, like, for instance, Diehick's events in 4-viva final state is one of the high-profile topics for round 3. So we are able to do it through the delay stream. We just store the events on tape and reconstruct them later when we can. Or the trigger level analysis stream, where you now do all the reconstructions at the HLT. There is no offline reconstruction, and what you get at the HLT is offline-like. You just write to tape. You can do it at a much higher rate because the events are so small. So this allows us to really trigger a high rate on very high cross-section processes, very low PT, covering a regime that is normally per scale away. Now, in the case of Atlas, I'm sure that's the case for CMS, Run 3 object reconstruction is not just Run 2 object reconstruction. We made major developments in basically all the object IDs. Some of them are substantial improvements. For instance, bit tagging efficiency is a factor of 2 higher at the highest PTs. You are trying to do dye-jet mass resonance searches. You have a factor of 4 more statistics than you had in Run 2, we expect to have. So now, of course, with early Run 3 data, it's very important to verify the good understanding of this improved object reconstruction, and this is, it's being monitored, it's been exercised, it's been proven to work. CMS has a similar, in spirit, small upgrades, but yet relevant upgrades for Run 3 as Atlas, the pixel, hand calorimeter, and trigger, in particular, a few others, with, again, the major upgrades upcoming for Run 4. So let me tell you about the phase 1 ones. The pixel detector, the phase 1 upgrade was already accomplished back in 2016, and that phase 1 upgrade detector operated during the hottest years of Run 2. Yet for run 3, during the LS2, the innermost barrel layer had to be replaced with a new detector because of the radiation damage that was sustained, and just to make sure we operate optimally for run 3. The detector is well commissioned and is being exercised as part of the full reconstruction. On the hadronic calorimeter side, I mean, the point of attention here is the barrel HCAL. The NCAP HCAL had been upgraded earlier on. So during LS2, this detector has had improvements to the sensors. The hybrid photodiodes were replaced by new silicon photomultipliers for better performance. And more importantly, perhaps, is the added longitudinal granularity to this calorimeter that now is going to be playing an important role to better reconstruct hadronic showers. As you know, particle flow, in the case of CMS, is an important part of the reconstruction, and like it is now for Atlas, but this information is only going to help. The detector is well commissioned, and now we're using collider data just to calibrate it in situ. And then on the trigger system, like Atlas, CMS has also had a number of highlights that are worth mentioning. Level 1, of course, we are talking about several phase 1 upgrades. This HCAL upgrade, for instance, includes timing information that now may become available. And on the high-level trigger side, we have similar enhancements in performance. CMS is making use of GPUs, HLT, to just offload a big chunk of the most expensive processing, and this is making room now to having, for instance, again, large radius tracking implemented at the HLT level. Again, the most performance offline reconstruction methods is also part of HLT, like graph neural network for jet tagging. And like Atlas, there are several streams. I mean, the main stream, the parking stream, we're now changing notation, is the same thing as the delay stream. 3 kilohertz CMS intends to collect large data sets of B-enriched processes in the kind of finite state signatures that are of interest to probe B anomalies. The scouting stream is like the trigger level analysis stream of Atlas, perhaps a bit more ambitious here. I mean, trying to get up to 30 kilohertz output rate, and again, trying to collect lots of statistics in regimes that were underpopulated or under-tested in run 2. So, like Atlas, CMS has achieved very good understanding of their physics object. I didn't find enough plots to make the case, but perhaps the best case is made by the first public result in run 3 by CMS. The first measurement of the TT-bar production cross-section at 13.6 TeV. This is, of course, important. It's an early result with just 1.2 inverse femtobarn fraction of the data set, but it gives you the opportunity to consolidate a good understanding of your reconstruction, the quality of the simulation. Here, CMS have, of course, since its early days, had to make a judicious choice of what channels to consider, dielectrons, lepton plus J final states, what event categorization to use so that you could in situ compensate for the not fully optimized yet uncertainties at the reconstruction level and be able to correct for effects that should be corrected, reduce the impact of uncertainties, and yet get not as ultra high precision measurement, but one that is quite interesting to see with about 8% total uncertainty in such an early measurement, in good agreement with the standard model. So this is, of course, a good achievement. All right, but this was 1.2 inverse femtobarn. I told you that we've been delivered, 38 inverse femtobarn or so far. Actually, the data collection efficiency is so good, it's not the best that it could be. It has been in the past, but we are getting there, 92%. So we have about a factor, of 30 more statistics that has been analyzed in the previous slide, ready to go. And in the case of LHCb, the data collection efficiency is a bit lower, but you should keep in mind that this is a new detector. It's a commissioning year, and is what is expected to be. Okay, so I'd like to spend a bit of time now telling you about the run 3 opportunities, what we foresee for the coming years. I mean, we're not talking about radiative corrections compared to run 2. I mean, it may seem so, but it's misleading. We're increasing a bit the center of mass energy. We're doubling the luminosity. We are going to get a lot out of that, much more than you would naively expect. But furthermore, we're dealing with much better detectors, better triggers. We're collecting data we never saw before. We are improving object reconstruction, as I mentioned, and we don't seem to be finding yet our ceiling in terms of, we thought we could not get any more from bit tagging in run 2. We are factor of 2 better rejection of the same efficiency now. And this seems to be ongoing all the time. We have improved simulations, not only of the detector itself, but also of physics processes, of course, thanks to the help from theorists and phenomenologists. Get the best simulations in place and work with us to understand our data, make use of it, to calibrate them. This will allow us a better understanding of backgrounds. We're going to be able to be more daring if we were not enough already with analysis and more aggressive. We keep finding new ideas, new directions that we never thought before, and we should be looking forward to combinations, not only across data sets. For instance, Atlas has reprocessed the whole run 2 data in Monte Carlo with the best algorithms that are used in run 3 so that we can combine both data sets seamlessly. And we get also the most out of run 2 in the process. But also combinations across experiments. We have a lot to gain by exercising this aspect. So okay, just a few examples of the physics program, some highlights that I chose myself. It may not be your favorite ones. But I mean, one of the, of course, interesting directions is exploring exotic matter more deeply. LHCb has discovered a big chunk of the 67 new hadrons have been observed for the first time at the LHC. Particular interest, because these are kind of exotic really, is tetraquarks and pentaquarks. Atlas and CMS are playing also a role there, are able to confirm, even study some of them. But I mean, we should be looking for this back to the 50s, probably to keep going for a while. We expect to discover perhaps more states, including big quarks here, that will make for relatively long-lived detectors, long-lived decays, that will benefit from the improvements on the detector to detect them and measure in detail their properties. We need to understand how do the quarks bind together in these exotic states. I mean, are they multi-quark bound states? They are molecular-like. There are rescattering effects. Theories think this may shed some light into some of the dynamics ongoing in the atomic nucleus. We will keep putting the standard model and the increasing pressure. I mean, we've seen a recent example of an area where a surprise came up with a new measurement of, for instance, of the CDF of the W mass, and LHC experiments, Atlas and LHCb so far, but CMS is coming up. We have a lot to say in terms of the precise W mass measurement. Hopefully, time energy crisis permitting, if we can collect the data set of low pi lab that we need for that. But we are going to keep going on, understanding our other precision measurements like the top mass. I mean, we are now at the limit of what theoretically we can perhaps understand what we're measuring. But also the whole program of EFT interpretation. We have a huge breadth of standard model, Higgs, top measurements, and we can put them together along with previous precision electrowave measurements to really constrain higher dimensional operators in ways that we never actually tackled before. On the flavor sector, on the other hand, as I mentioned, LHCb has done a lot already on CP violation and mixing. With the new detector and data sets, we expect in factors of 2 to 4 improvement in the precision of those measurements. So this CKM triangle will change from here to here. You see the much thinner band here for a measurement of this gamma angle. You see the constrained parameter in demixing compared to the one we have from run 2 at the end of run 3. So this is going to keep ongoing. We are hoping perhaps to take a first look at the Higgs potential in some sense. You have followed a bit this field. There's been amazing developments on the di-Higgs search program, factors of n from iteration to iteration of the analysis, well beyond luminosity scaling. To the point where the latest combinations by Atlas and CMS are a 3 times standard model, the limit on the cross-section for di-Higgs production. But then you just need to look at, you thought this is the best of run 2. You just need to compare the spectral limits between Atlas and CMS in some of the leading channels. The 2 experiments differ quite a bit in sensitivity. So it means that the one that didn't do so well can do much better, and vice versa, right, for the other channel. So we should expect this could be actually better. And we have the opportunity with the reanalysis run 2 and into run 3 to double the statistics, improve the methods, and perhaps achieve standard model sensitivity already in run 3. Probe at the 2 sigma level, if you wish. There's a new interaction we've never seen before. And now when it comes to interpretation, you can bring in the precise single Higgs measurement program to have model-independent interpretation of the triple Higgs coupling. Now, we expect also to consolidate discoveries we expected to make. We have already achieved evidence for Higgs to mu for 4-top production. If we keep on this rising curve, we expect to achieve observation, hopefully during run 3. This increased statistics of this process and perhaps others. This increased statistics will allow for first differential cross-section measurements. But hopefully we'll also achieve observation of discoveries we didn't expect. And these flavor anomalies are perhaps a good example of something unexpected that is being consolidated, and we don't know what's going to happen. But what we know is that LHCb is going to be a main driver force there. But Atlas and CMS has a lot to say. You can see on this program of rare BDKs, CMS has competitive sensitivity in the latest result with LHCb. So there are some parts of the program where you have 3 experiments, not 1. Okay? But with these increased statistics and improvements, we hope maybe, and we're crossing the fingers, that we will confirm at least some of the B anomalies and perhaps start measuring or at least getting some information about the nature of this interaction. We're talking about V minus A, purely vector. What are the implications for explanations beyond what we already are guessing? In this area of lepton flavor universality hints, there are many beyond LHCb. The G minus 2 you can consider. There are the Cabibbo angle anomalies. Several of them. Theorists have been quite busy proposing explanations, and Atlas and CMS is taking this seriously. We are trying to make sure we don't miss something obvious. It would be a pity that 10 years from now, say, okay, you should have discovered that particle that was there already, had sensitivity. So we have a very aggressive program of searches for leptoquarks, heavy vector resonances, new scalars, new fermions. And of course, we take inspiration in that program into what are some of the suggested directions that may be more explanatory. So for run 3, we expect this program to be developed. At the end of run 2, we are already getting very ambitious with leptoquarks, some of the more exciting channels that are, and where we are showing that we can start probing into the phase space, the parameter space region that could explain the B anomalies if real. We are already getting there with our searches. In fact, it's interesting that the CMS had an excess right where it would be expected for a heavy vector leptoquark that mostly produced through T-channel exchange. We'll see whether this is consolidated and in run 3. But nevertheless, this program will be just not looking for this, will be broadened more generally to all possible kinds of leptoquarks. We're going to be following up in this spirit of, okay, maybe we are missing an opportunity here. We had some anomalies, deviations in the high mass Drell-Yang searches, where you have excesses in dilepton plus B jets in the tail. You have a apparent small lepton flavor universality violation in high mass Drell-Yang, from CMS. There's an Atlas result coming up soon. Okay, we're going to broaden this program. All dilepton final state, inclusive and exclusive, differentially, LFUV ratio-tase, make sure that never mind what LHCb might be seeing, we are not missing something obvious. But Atlas and CMS have many excesses of their own. If you didn't pay attention, there are many 3 sigma level excesses out there. Just display some of them. Global significance may be low, but we just need one of them to be real, to be in business. Okay, and okay, I just have 3 more slides and I'll be done. But beyond just ambulance chasing, if you wish, we also have trying to make sure we are not leaving anything else uncovered. LHC is about energy frontier, heavy objects. Okay, we're making sure we're looking to line new physics. We have developed many successful strategies in run 2 in terms of reconstruction and trigger to probe these low mass regimes. In run 3, I just told you about the increased order magnitude increase in hadronic yields by LHCb that will allow to test previously uncovered regions of phase space, for instance, for very light dark photons. Atlas and CMS is just they've been through these trigger upgrades, expanding the scouting program. I told you in the past we were running trigger level analysis on digests and dimuons at best. Now we do it for all leptons, for photons, for B jets, for dark sector jets. We're going to be probing much better there, and also using data parking, quite effectively. Also, the lifetime frontier. I mean, we did quite a bit of lonely particles in run 2, but I mean, with some crutches there. We were largely relying on standard triggers, high emissivity trigger, prompt triggers, and then just for just a few LLP triggers genuinely in the system. For run 3, we have undergone a kind of an LLP upgrade. We talk about the innovations in reconstruction in terms of less radio striking in ATLAS, the trigger developments in CMS that will allow to have LLP triggers with timing, LRT also at the HLT, and a whole suite of new triggers that are probing for displaced particles that we didn't have before. And so again, this is brand new data sets we have not tested in run 2. And finally, just making sure we don't miss something we didn't expect because we had not thought about it. Of course, the model agnostic searches are a good way to complement the direct search program, which nevertheless cannot cover all possible final state signatures. So there's going to be gaps in coverage. And in the past, we've developed this kind of general analysis that have hundreds of final states that are being tested with less precision, but more exhaustively, perhaps, than direct searches. Nowadays, the new kid in the block is anomaly detection. And machine learning-based anomaly detection, both at the object level and at the event level, are now areas of intense development in high-energy physics. And so far, very few analyses have made use of these new developments. We should foresee significantly increased use of them throughout run 3 to make sure we don't miss the unexpected. So just wrapping up, as I mentioned, first year of run 3 could hardly imagine a better starting point. Sure, accidents may have not happened, but still very spectacular on the LHC and experiment fronts. Run 3, don't just think it's going to be more the same. It's going to be different in many ways, through the increased center of mass energy and luminosity, the better detector, the much larger data set of things we never tested before through the new trigger developments. We are going to be beating, like we've done in the past, it's a kind of a waste of time to do extrapolation exercises because they are demonstrating over and over that they were pessimistic. So we are beating luminosity scaling through a combination of improving reconstruction, simulation, analysis strategies over and over because data makes us smarter. We have an extremely rich physics program that keeps being optimized, where new hot topics get added, and where we, as a community, need to keep thinking about what is the most we can get out of it. This is part of the plan right now. A discovery really may be around the corner, and we think this is a good investment and perhaps the best, one of the most productive uses we are going to make of run 3 in the coming years. But again, perhaps things are going to go differently. Finding new physics may be more like running a marathon. We should be ready for it. And on the bright side, the good news is run 3 is just 10% of the data we're going to be collecting. So I think we should be all quite excited, about the upcoming ride. Thank you very much.
Thank you. Thank you very much for this nice overview of LHCb outcome. So, please, there. We are running really out of time, but we have time for a couple of questions. Please.
Very nice overview. What is the general strategy about the evaluation of the new data? Will you wait until you have accumulated like in run 2 and then do the analysis, or is there a general plan? Or
yeah, I mean, no. The evaluation, but you mean checking that everything is working?
No, I mean
calibration.
new measurements with the new data.
Well, there are different plans. There are parts of the program where the new data, like 38 in femtoban, represent a small addition to run 3. Yet, we are talking about, in some cases, about very sophisticated analysis. So you should start early because just putting in place a run 3 analysis, it goes beyond just let me run over the n tuples. You need to have the calibrations. You need to have all the technical steps, sorted out. And so this is starting. There are many analyses that are already ongoing. At what point they will deliver a public result, if it's a conf node with partial run 3, just to demonstrate things are understood, or it's going to be a partial combination with run 2. There are different kind of analyses. The ones with new triggers will aim at the first result with only run 3 even as early as possible. And hopefully by Morion, we're going to see some of them and throughout summer next year as well.
Is there any more question here?
Just very fast comment. You have talked about long-living particles for Atlas and CMS, but I think it is important that LHCb is also contributing, and Santiago and Valencia, in fact, with the new trigger strategies at LHCb, I think we have a significant contribution. Just a comment.
Yeah, no, thanks for that remark. Absolutely.
Okay, thanks for the very nice talk. Okay, you mentioned briefly the WMAS. Okay, there was a hot topic about 1 year ago. Okay, so and now we are going to high luminosity, and we know this is tricky for precision measurement, for a precision measurement like this one. So, can you comment on the plans for precise measurements during run 3? And then I will ask later to our, sorry to interrupt you. So then I will ask later to our CMS colleague why there is no CMS point in that.
Yeah, no, I think the first thing, there's not a lot I can say about that, but I mean, you should expect that there's going to be a CMS point. Okay, so that is going to be interesting by itself, and it's going to be, just judging from past experience, CMS doesn't do a poor job, right? So it's going to be a good measurement that's going to be informative. We're going to see. For run 3, I have not followed this personally very closely, but of course, as you mentioned, high luminosity is a problem. You need to have low pileup to really do a good job at the WMAS. There is discussions ongoing, and I understand that Atlas and CMS are in agreement. They would like to have a 1 femtobarn of mu equals 2 data. Low pileup, no, that may take a month to collect. Are we going to be able to, because of the cuts due to energy crisis, are going to be able to afford it? Are we going to be able to convince each other that that's, I think this discussion is ongoing. But what's known is what's going to be needed. With 1 inverse femtobarn, you can achieve good sensitivity. Statistical uncertainty is below 10 MeV. So now the question is what the systematics are. I mean, okay, but you are in a low pileup regime. You could expect to do no worse than you did in the past. So these measurements, I think, are going to be important, that we try to do them in run 3. The question is whether we can accommodate the required luminosity at the low pileup. And this is going to be an ongoing discussion. I know that at least 2 experiments are in agreement that this is worthwhile, but the discussion is ongoing with new developments because of what we know, right, about the energy crisis and so on.
Is there a last question? No? So, otherwise, we will thank again Aurelio. And the next speaker is Carlos Hoyos. So, Carlos Hoyos is going to tell us about holography applied to nuclear physics and astrophysics. So, is everything ready?
It's working, huh? Yeah.
It seems. So, everything is working, so please, your floor, you can start. You have 30 minutes.
Okay, this is the pointer. Okay. Okay, yeah, first let me thank the organizers for inviting me to talk here. I'm going to talk about some recent developments in applications of holography to very dense matter in the sense of large baryon density. This has been motivated by ongoing progress in astrophysics, in observations of the properties of neutron stars. So let me start with that. So a neutron star is like very small compared to the size of normal stars object, and it its mass is typically between 1 and 2 solar masses, so something which is average is 1.4 solar masses. So it's heavier than our own sun, but it only has a radius of about 10 kilometers, so it's about the size of the Bilbao metropolitan area. So you can imagine that this object is really, really dense. Okay? The density is of the order of the density of the nucleus, of the atomic nucleus. And at the core, it can even go beyond that. It can be a few times larger or even an order of magnitude larger. So this is a very extreme object, and it has very extreme conditions for the matter inside. So the matter that is at the core, the phase it is in, the state that we can find there, it cannot be found anywhere else in the present universe. So it's quite interesting, at least well, for astrophysics and for the theoretical point of view, to try to describe this state of matter. Now, from these astrophysical observations, we can infer some of the properties of this matter inside the star. So the way it works is something like this. Imagine that we knew the equation of state of the system, so that means we know the pressure as a function of the density or the energy density. And then here you see a lot of curves. So those correspond to different models for nuclear matter. Okay, so all these labels correspond to different models, and each of them has a different equation of state. Now, if you take a given curve here, a given equation of state, and you plug it into the Einstein equations for the star, then it speeds something which is the mass and the radius of the star. And you can do this several times by changing the central value of the density. So you change the density at the core, and then the density starts here, and then it goes down as you go to the surface until the pressure goes to 0. And then you keep changing this density at the core, and then you are at one point on this curve, and then you keep moving on this curve, and then you end up having these mass versus radius curves. So for each equation of state, the Einstein equations give you a different mass versus radius curve. Now you can go through the inverse process. So you can observe this mass and radius of the stars, and then from this go back and try to get what is the equation of state. So if you have many points on this curve, you can, in principle, reproduce the equation of state, and then you know about the phase of matter. Okay, so of course, the challenge is to measure this mass and radius in some accurate way. Now, the developments that have been come from different directions. So one of them is coming from pulsars. So pulsars are neutron stars that rotate very quickly. And they typically have a strong magnetic field, so the radiation is collimated along some beams. So when the beam is pointing towards Earth, what we see is like some pulsating increase and decrease of radiation. No? So that corresponds to the pulsar rotation. Now, if this pulsar is in some binary system, when the pulsar is behind the companion, then there is some delay produced by gravity from the pulsar, from the pulse that is coming to us. This is called Shapiro delay. And from this one can make very precise mass measurements. And one of the masses that were measured in this way was mass for a neutron star that was like 2 solar masses. So this is a quite heavy object for a neutron star. And in fact, it imposes already strong constraints on the equation of state you could have. Okay? Because some equations of state predict masses that will be below these 2 solar masses. No? For instance, this line here doesn't reach 2 solar masses, so that equation of state will be excluded by that. Now, a more recent source of observations comes from this so-called NICER experiment. So that's a neutron interior experiment composing, okay, I don't remember exactly. But it's essentially what it's measuring X-rays coming from some neutron star. It's making a spectroscopy of that, and then it can determine where these spots where the beams are located are on the star. So it can find what is the relative position and the shape. And from this, you can infer the radius of the star. Okay, so this is a very, by other means, this is a very difficult measurement because the star is, as I said, only like 10 kilometers in radius. So if you try to see it with a telescope, you won't see anything because it's too small to resolve it. So this is essentially maybe the only way to measure the radius in some accurate way. Okay, and then if you also have the mass, then you can really constrain the equation of a state. Now, a third source of observations is coming from gravitational waves in binary mergers. So you can have two neutron stars rotating around each other. And this system is losing energy and angular momentum through the emission of gravitational waves. Okay, so this happens in a long time, but when the stars come very close to each other, then it starts happening more quickly until they collide and merge. Okay? So there is a difference so this happens also for black holes, but there is a difference between the neutron stars and the black holes. And the difference is that, in principle, the matter that is forming the neutron star can be squeezed by the tidal forces produced by the other star. And that is going to change the shape of the star, and that is also going to affect the gravitational radiation that is emitted from the star. Okay, so you can have a signature in the gravitational wave that you measure of this deformation of the star, and that is encoded in this tidal deformability, which is also a quantity that is determined by the equation of a state of the star. Okay, so there have been so far a couple of binary mergers of neutron stars in 2017 and 2019, and there has been some merger with a black hole. So there is some information that is coming also from here. Okay, so if we collect all these constraints in the masses and radiuses of the stars, then we can constrain the equation of a state. Okay, so here there is an example of how this will look. So on the left side, you have the equation of a state, or possible equations of a state. And here is the pressure, here is the energy density, and then this purple band will correspond to low energy nuclear matter physics. So you can have some nuclear matter models or use chiral perturbation theory to fit nuclear matter experiments. And then you have a more or less precise description of nuclear matter at these densities. Okay, so you have some information coming from the low density part of nuclear matter. At very high densities, you can use perturbative QCD. So you can also have some information from first principles of how the equation of a state should look. And then in between, well, you don't know what is the equation of a state. So what people has done here is they consider modeling the equation of a state using polytropes, so piecewise polytropes. And then they consider like a whole family, like tens of thousands of equations of states constructed in this way. And then they pose several physical constraints on them, like you should have causality, so the speed of sound shouldn't be above the speed of light. The system has to be thermodynamically stable. And then that gives you something like these dashed lines here. And you also impose that it interpolates between these two behaviors. And with these dashed lines, you find that the mass versus radius curves in this right side will fall inside this region inside the dash area. Now, when you impose the astrophysical constraints, then you reduce the possible equations of a state. So you end up only with the color part of this band. And here you reduce the mass and versus radius curves. No? So they have to fall inside this color region. Okay, here the color regions corresponds to, the different colors correspond to different stiffness of the equation of a state. Okay, so here you see in practice how the astrophysical constraints act on this equation of a state. Now, what do we know about matter at these extreme densities? No? We now can constrain it from the experiments, but as physicists, we want to have a microscopic model that tells us what is the behavior and why this is the behavior and what kind of matter we have. Now, this is a cartoon of the QCD phase diagram. Okay, so you see here several, well, this is the temperature axis, and this is the baryon chemical potential axis. So you see here plot several possible phases that you can have. At low temperature and low chemical potential, QCD is a confining theory, so you have just hadrons. You can have a hadron gas. If you increase the density, at some point you reach the density of nuclear matter, and then there is a first-order phase transition at low temperatures. If you increase the temperature, then you deconfine, and then you have a quark-gluon plasma. Okay, so quarks and gluons are more or less free to move. And then there could be some line of first-order phase transition separating these two phases at finite chemical potential that will end at some critical point. Now, if you go to very large chemical potential, we know from perturbative QCD that the state of matter should be a color superconductor, some color flavor locking state. So you should have also this phase around here. And it can be separated from, let's say, the quark-gluon plasma from another kind of phase transition. Okay, so this is more or less how the QCD phase diagram we think it should look like. Now, what do we really know about this? Well, from experiments, we can access some part of this phase diagram. So for instance, from the cosmological evolution of the universe, we start at very high temperatures, then we lower the temperature and increase the baryon density. So we follow more or less this line. And then in colliders that collide heavy ions, then we can access also this quark-gluon plasma at temperatures close to the crossover temperature. No? So nowadays, the experiments are trying to explore higher densities to see if they can reach this critical point that I was showing in the previous diagram. No? But essentially, the heavy ion collisions are exploring this region of the phase diagram. And then neutron stars will fall somewhere around this part. Okay? So density is larger than the nuclear matter density, and then low temperatures relative to the quark-gluon plasma. Okay? So as I said, so far, this kind of matter can only be found inside these neutron stars. Now, from the theory point of view, then we can use perturbation theory with coupling when the temperature or the chemical potential are very large. So this region can be described using weak coupling methods. Now, at low temperatures or chemical potential, we have these nuclear matter models or chiral perturbation theory. But they are effective theories. As such, they are only valid up to some scale. Okay? And when we reach this scale, essentially, the effective theory breaks down. And this happens, for the chiral perturbation theory, essentially at the saturation density. So this will tell us something about the outer layers of the neutron star, but at these heavy stars where the core is at densities larger than this, then we cannot apply chiral perturbation theory or these other models. We have a non-perturbative first principle method, which is lattice QCD. No? It consists of doing numerical calculations of the gauge theory. But it has some problem when we introduce baryon chemical potential. Okay? So essentially, it's numerically exponentially costly to try to compute anything at finite chemical potential. So lattice QCD is constrained to regions close to the temperature axis where we can do some perturbative expansion in mu. And then in all this region in between, which includes the region which is interesting for neutron stars, we can only use phenomenological models. In fact, all this part of the phase diagram that I was plotting here is coming from these phenomenological models. It's not something that we know for certain, but it's an educated guess that we will have this kind of transitions or critical points, but it's not guaranteed by the theory. Now, it's in this region where coupling is not weak, where we have finite density and finite temperature, where holography might be useful. Okay? So this is where we want to use holography to describe this region. Now, let me tell you something about holography, in case you're not familiar with it. First of all, it's a duality. So this means that we can describe the same physical observables with two different theories, or the same object in two different ways. No? So an analogy is this picture. So this picture can be described as two white faces facing each other in a black background, or a black vase in a white background. No? So these are two completely different descriptions, but it's the same picture. So the same happens when we talk about duality in these quantum field theories. Now, the holographic duality, one nice thing it has is that it's a duality between a weak coupling, a theory which is at weak coupling, and another one which is at a strong coupling. So if we have a strongly coupled gauge theory, the dual theory will be weakly coupled, and the converse will also be true. Okay, so because this region of the phase diagram is not at weak coupling, we cannot use perturbation theory, then the holographic duality may be useful there because of this property. Now, in more detail, this is a cartoon of how the duality works. So the idea is that there is some space, and this space has a larger number of dimensions than the space where the field theory lives. So if we live in 4 dimensions, 4 space-time dimensions, our dual theory, which is a theory of gravity, will live in a higher dimensional, at least 5 dimensions or more. Okay? And then we can think about the field theory as living, in some sense, at the boundary of this space. Okay? So we can describe observables at this boundary, this, let's say, the equation of a state of the field theory at this boundary, using some weakly coupled description of gravity in the interior of this space. So that will be the holographic duality. Originally, the boundary theory was a conformal field theory, and the interior was anti-de Sitter space. But this can be generalized to non-conformal theories and confining theories and so on. Okay, so I will show you some of the results of using this duality. I'm not going to delve into the details of how this was computed, because I guess it's interesting for the experts, but not in general. I will just show what kind of results you can get. So first, you can get equations of a state using holography. And I'm just going to show like the most advanced equations of a state that people have constructed. So here, the equation of a state is composed of the different pieces. It was, let's say, constructed by these people. At low energy densities, you use nuclear matter models, like this purple band I showed you in the previous plot. And then after some density, where these nuclear matter models are no longer applicable, then you use the holographic theory. Okay? And this holographic theory is valid all the way up to the region where you will use perturbative QCD. And you make it in such a way that at the density where you transition from the ordinary nuclear matter model to the holographic model, this happens in a continuous way, and that also happens when you go to the perturbative regime. Okay, so in these holographic models, there are 2 phases that can be described. So one of them is a kind of nuclear matter phase, similar to the one you have at low densities. And then there can be a phase transition. So here we see first order because there is a jump in the energy density, which this gives us the latent heat of the first order phase transition. And then you go to quark matter. Now, the different colors correspond to imposing different kind of constraints from the astrophysical observations. Okay? And then you have some freedom in choosing where this change from the nuclear matter model to the holographic model happens, or you have also some freedom when you match to, for instance, lattice QCD results, this model, then not all the parameters are completely fixed, so there is some freedom in the model. Now, from this, you can reproduce the mass versus radius curve, where you have imposed the different astrophysical constraints, and you see that they can all be satisfied. So this is a viable holographic model to describing the holographic equation of a state. Now, another different model proposed by these people is a bit different in the sense that it doesn't contain the phase transition to quark matter. It only describes holographic nuclear matter. And then you see that the behavior is quite different. So this will be like the low energy part, which is fitted to the ordinary field theory. And then it has like some quick increase of the equation of a state in this way. And contrary to the other model, this model is not fit to match perturbative QCD at high density. So we should take this model to be valid only below some energy density. No? More or less, this point will be already excluded, probably. Now, when one plots the mass versus radius curves of these different holographic models, you see that, for instance, this green line doesn't reach 2 solar masses, so this will be excluded. But then these other lines can satisfy the constraints from astrophysics. Okay. Now, one interesting point about this model with the quark matter phase transition is that because this first order transition is very strong, the star becomes unstable when you start producing quark matter at the core. No, so this model will predict that there is no quark matter at the core of these neutron stars. On the other hand, some people propose that because of this, there is some kind of change of slope in this band. Some people propose that the change of slope corresponds to quark matter. So there is some discussion in the community regarding whether there is quark matter or not. No? There are, depending on how you want to interpret the change of behavior of this equation of a state. Now, another kind of work that has been done using holographic models is to do merger simulations. So this binary system that was rotating until the two stars collide with each other. So here I'm showing snapshots of some simulation. Here you see at the beginning the two neutron stars, and then they collide and they produce some dense region localized at the collision point, and eventually this will either collapse to a black hole or form another neutron star. And below you see what is the gravitational wave signal produced by this merger that is plotted above. Now, nowadays in the experiments, we can only measure this part of the wave because the frequency here and the amplitude are such that they fall outside the sensitivity of the gravitational wave detectors that we have at present. Okay, but maybe in the future, it will be possible to measure also this post-merger phase, and this will give us more information about the star because there are some characteristic frequencies that appear in the post-merger phase that are also directly related to the properties of the equation of a state. Now, this is another merger simulation from a different group. Now, in this case, here we have plots of different quantities, and like the density or the temperature or the quark fraction. And then what you see around these dashed lines is they are surrounding the regions where you had the phase transition from nuclear matter to quark matter. Okay, so in these merger simulations, you will have a prediction that quark matter was produced during the merger. Okay, and then if you explore, what is the state of the matter at different times during the merger, then you can see this will be the early times. Then what you see is that basically the matter starts being very hot. Then at middle times it cools down, but it becomes more dense. And at late times it becomes cold and dense. Okay, so during the merger you are exploring different parts of the phase diagram, and then you can see if you go from a confined phase to a mixed phase and to the deconfined phase. Okay, so this tells us that if we know exactly how the equation of a state behaves, we can have some predictions about how the merger will evolve through these phases. Now, finally, we can compute transport coefficients. These are of interest for instance, if you have a star, a quiescent star, then this could be interesting to see what is the cooling rate of the star. Or when you have a merger, this could be interesting to see how the different quantities are evolving in a hydrodynamic evolution of the merger. Okay, so this was actually computed by some collaborators and myself. And we then use the two models I showed you we use one of them. This will be the red line, but we only explore quark matter, not nuclear matter. And then we use another different kind of model, holographic model, which is less realistic than the one I was showing you. And so that will be these dark green lines. And then we compare that with perturbative QCD results, which are the green bands. Now, what we see is that compared to the perturbative predictions, that is what people has been used so far, the holographic models can predict a very different, even qualitative behavior of the transport coefficients. Okay? So this means that we shouldn't expect at this strongly coupled regime that these perturbative QCD calculations are going to give us any accurate description of the transport. Okay? Instead, we should explore more these strongly coupled theories and see if we can find some at least qualitative behavior for these models. Okay? So here we see, for instance, that the conductivity, the electrical or thermal conductivity, are going down, while in the perturbative case, they go up. No? And they differ by orders of magnitude, even. And for the shear viscosity, is also the case that they have a completely different behavior. Okay? So this gives us some new insights about the properties of this strongly coupled quark matter. Okay, so this is more or less the summary of the results that we have so far in this line of research. Now, there are some future directions that we would like to pursue. So some of them are related to this transport. Essentially, there is something called the Armode instability of the neutron stars. This means that stars that rotate very fast, because of the coupling to the gravitational waves, they can lose angular momentum very quickly. There is some kind of feedback. And this can only be stopped if the bulk viscosity is large enough to damp oscillations of the star. Okay? So this depends actually on the equation of state, and is something we want to find out for these holographic models, how this dampening can happen. If this didn't happen, then there wouldn't be these fast rotating pulsars. Okay? So it's necessary that there is an enhancement of this bulk viscosity. Now, of course, I told you about the transport coefficients in merger simulations. These need to be extended to include the nuclear matter phase, and also more realistic equations of state, and for finite temperature, different quark fractions, and so on. Now, another interesting direction will be to study different phases of the matter inside the star. So far, I just discussed either ordinary homogeneous nuclear matter or deconfined quark matter, but without any symmetry breaking or pairing of the quarks. Now, but we know that at very high densities, there's going to be some superconducting phase, and maybe in the interior of the star, we can also have these kind of phases. No? We know, for instance, in nuclear matter, that there should be some neutron superfluid inside the star. So all this should also be described within these holographic models. We know in principle how to do this. We just have to start doing it for realistic models. And then other interesting quantities are neutrino and photon production rates. So this gives you information about the cooling of the star. No? That is interesting for the evolution of the merger, or essentially the evolution of the star after formation, and also eventually for astrophysical observations where you see how much heat is radiated by the star from by observing the radiation that is produced at the surface. Okay, so these are some of the directions where these holographic models could be extended. Okay, thank you.
Thank you very much for this talk, perfectly on time.
Thanks.
So now we have time for questions. Is there any question?
Me first?
Hi, thank you. So, holographic models are also phenomenological, in the sense that they are not top-down, so you have parameters that you adjust. Mm-hmm. Now, my question is, how do holographic models compare to other phenomenological models in the same region? For instance, is there any signature of holographic models that is absent from other phenomenological models? Is there some way that, well, with observations we can conclude that holography is the right way to describe the interior of the neutron star? Or do you have enough parameter range that you can fit the behavior with different models?
Yeah. So what I will say is that so far we don't have enough information to, prefer one over the others. Because what we know mostly about these stars is the question, well, we know some constraints on the equation of state, and both phenomenological models and other phenomenological models like the holographic models can, satisfy these constraints. No? So in principle, this is not enough to discern between the two, right? Then the question is if in the future we will be able to have some more fine observables that are related, for instance, to transport, right? And there one can possibly observe differences between the holographic models and these other phenomenological models, no? Because essentially, even if the equations of state are similar, one expects transport coefficients they don't have to be similar between different models at all. And if we have enough information to, let's say, determine several of these transport coefficients, then I think that will be quite constraining for all the models. It doesn't mean that the holographic model has to be the right one, but at least it might be enough information to discriminate more between these kind of models. Yep. So far, I guess one of the advantages of the holographic model is that some of these calculations are easier to do in the holographic models, no? Like the transport calculations. And so you can, in principle, do many calculations in these holographic models and see if you see some kind of universality appearing in the transport or something like that that can tell you, give you some more general information about the stars. No?
Okay, I have another question. Just for completeness, no, concerning when you have discussed the experimental efforts, no, to constrain the equation of state for dense nuclear matter, you have mentioned colliders where there you mostly populate high temperatures, low densities, as you have shown. Probably this is not so relevant for your problem here, but you have not mentioned other efforts, other programs we have, for example, at FAIR, at lower energies, where you using neutron-rich projectiles, we are producing neutron-rich matter at high densities, 2-3 times saturation density, and probably this is a bit more relevant for your case. And
but probably those are higher temperatures, maybe?
No, these are moderate temperatures, high densities, where you go if you run the collision at lower energies. And yeah, my question was a bit related to the previous one is, for example, you know that when using probably phenomenological models, one of the main problems of these models is when trying to describe hyperonic matter inside the neutron star, no? Because strangeness soften the equation of state, and then you don't produce any more so heavy masses. So how this problem is treated in your approach, or how do you deal with this?
Yeah. Okay, here, I guess I should mention that this model so far is made with, let's say, 0 quark masses. Okay, so then there is no difference between different flavors. Okay, so one of the things that one has to do is to add masses to the model. This is something people is doing now, and have different masses for up, down, and strains. And then you can start distinguishing about this a condensation of different, or appearance of different flavors, no, in the nuclear matter. Okay, so this is a good question, but so far this has not been addressed in the holographic models.
Have you several times spoken about the realistic, less realistic holographic models? Is this what you mean? This sort of...
Yeah, so this model, for instance, at zero density, at zero chemical potential, has been fit to lattice QCD. Okay, so you reproduce the equation of state from lattice QCD and some of the observables that you can compute with the holographic model. So you try to fit as much as you can to the data that you have at zero chemical potential, and you introduce the chemical potential and try to see what the model is telling you.
Is there any more question? No one? Okay, let's thank again Carlos.
Thank you.
And it's time to move on. It's the last speaker today. This session is José Antonio Lai. And José Antonio is going to talk about nuclear structure and how low experimental experiments can tell us something about this. So, José Antonio, you have 30 minutes. Please, go ahead.
Okay. Is this working? Yes. Okay, so, well, good morning, everybody. Let me start thanking the organization for having me here. It's a pleasure to stay here today in Bilbao to talk to you a little bit about nuclear reaction theory. And I will not cover, or I will not do an overview, proper overview of the things we do in the community, because I would like to discuss a little bit, let me, maybe better, three successful stories that I think we have done in the community recently, and that also have a common thread that I will discuss a little bit. And to compensate, instead of conclusions, we will have some perspective or some ideas of how we are moving forward in this topic. So this is what we want to do. And so we work on nuclear reaction, but our goal somehow is to learn a little bit about nuclear strata. And so nuclear strata, the problem is that it's only the tip of the iceberg. So if you want to go to study, for example, in this case, beryllium-11, what you do is to throw it through something like lead, and then you have to take a little bit care of what is going in the nuclear reaction, okay? But this is risky because somehow you're adding a certain complexity, okay? So you always want to stay nearby or to solve this problem without getting involved in this problematic complexity. But there are some crazy people that we are happy with this complexity because we see its inner beauty there. No? But we are not so crazy. We work on, or most of our community work on direct reactions. Okay, what means direct reaction? Precisely that you stay into situations where only few degrees of freedom, only few things are relevant or are excited along the reaction. Okay. And you expect with that there is a one-to-one relation between the thing you want, the strata, and the thing you measure, okay? So you don't go too deep, because the thing you measure, the cross-section, you want to relate it to the observable you are looking for, okay? But this somehow has a certain approximations involved there, and then you, in this approximation, you lose some accuracy. Sometimes you can only say something qualitative, or something quantitative, but without the desired accuracy. No? And our effort right now is to look for or to search for this accuracy, and this means that you have to increase the complexity at some point without losing track. Okay, so we are going to we have to deal with this, and we are getting a little bit deeper and deeper so that we get a nuclear strata with a better accuracy. I will try to follow in in the three topics that I'm going to talk. The first one is double charge exchange reactions. And in this case, the motivation is mainly the neutrinoless double beta decay. I think I have to say very little here because you all know that you can have a nucleus. This is something that we can measure. The two neutrons can become two protons, and then they emit double bosons that eventually you see two electrons, and you also see the neutrinos. No? So this is something you know, that they can be a double beta decay with two neutrinos. And if the neutrino is its own counterparticles, you can also have the neutrinoless double beta decay that is more rare, but it's something we are trying to search and try to find, because then through the decay rate, you can access certain information also on the mass of the neutrino. You will see, or you will demonstrate that the neutrino is imaginary particle, and so you know. No? The main thing here, or the main problem, is that you have some factors here, and there is a nuclear matrix element that we have a little problem there. No? Nuclear models, as you may know, they disagree on the value of the nuclear on this matrix element by a factor that can be around 3, but the problem is that it goes to the square, so that means 1 order of magnitude in the half-life. And then when you are investing so much effort and money in order to find this decay, so having this kind of uncertainty is not something that we would like, right? And the only way to improve this situation is to constrain these nuclear starter models. And in order to constrain, or in order to fine-tune your model, what you want is experimental data. But we don't have this data. We have to search for other alternatives. One alternative is the double charge exchange reaction, which is mainly the Numen project in which we are collaborating in for the theory part. And so in the LNS laboratory at Catania in Italy, they are performing reactions like this. So you send, for example, neon 20. If you measure after the reaction oxygen 20, this is going to be one of your nuclei that you know that undergoes this double beta decay. And so if you do this, so you will end up having 2 more protons. So this is the equivalent to a beta minus beta minus. But in nuclear reaction, we can do the opposite direction. So we have also oxygen 18. You see the product of the decay, and you undergo the beta plus, for example. No? So we have these two. These are the two options that, after thinking a little bit, there were the desired proofs that they are trying to measure there. No? And now we can, so this is analog to the double beta decay, but then we can start discuss how similar, what are the similarities and differences, and this is a lot of things to discuss. There are a lot of discussion here, but the main one is that now the mechanism is governed by the strong interaction, and it's not the weak interaction. But this is precisely what you want, because strong interaction means that you are going to have more probability. So this is something you are going to measure. Otherwise it's quite hard, and this is because this is the reason why we are not sure about the discovery, or we haven't found the neutrinos double beta decay, right? So then the operator after this, so the operator, the initial and final state is the same. How similar, how different is the operator, it can be discussed, but there has been found a certain proportionality. And then I'm going to focus on some of the drawbacks that we have, or we think we have solved. The drawbacks is that in the reaction, you can arrive from, for example, if you start at the germanium and you want to go to the selenium, what you want your nucleus is to go directly here by performing a double charge exchange, so that two neutrons here become 2 protons. But the nucleus can do whatever they want, okay? So you have that the total cross-section is not only this. It's going to be a little bit of getting 2 protons and losing 2 neutrons, getting 1 neutron, do 1 single charge exchange, and then here, okay? And in the cross-section is all these paths modulus to the square. So you also need the interference, which is another complexity. Going one by one, so this is the one that you want, where somehow you have 2 nucleons or 2 neutrons in your project type, in your target, for example, that becomes 2 protons. No? I said 2 neutrons, 2 protons. No? And this implies that in the projectile, they go the other way around. And this is somehow what you can relate to the neutrinoless double beta decay. So the 2 protons come at the same place. Okay, this is what we call a Majorana double charge exchange. Okay, and the other one is going one by one. So you can first get one charge exchange and then the next one, and you somehow travel a little bit along the intermediate states. Okay, so this is something that we can compare with the 2 neutrinos double beta decay. Okay, and so this is somehow the information you want, but you have more. Okay, you have the effect of transfer, and with transfer you can do a lot of things. But this is something that we've been looking at carefully. You know? So if you try to go from here to here without any charge chain, this is what we call multinucleon transfer, and we have already checked that this is orders and orders of magnitude smaller. So it's already ruled out. If you combine transfer with some single charge chain here, so basically you can go here and do this, or you can here and there. There is still some chance, so there is still some contribution, but our estimation is below the 1%. But it's something that we are looking to model and to include in the comparison. This is something that we are working on right now. This is the situation right now for a case that is not maybe of interest for the double beta decay, because this is calcium-14, but it's the same thing, and this is our this was our benchmark, okay? And the 2 lines here are the calculations for the Majorana and the sequential, no? So somehow for the without neutrinos like and with neutrinos like, okay? There is a little bit difference here, because so far we have the sequential under control. We know the absolute value. We know very good and this is the green line, okay? This is the green line, no? And you see that there is still certain deviation from the data, and this is the room for the other one, for the Majorana part, because we are actually somehow we are running out everything else. We have strongly studied all the other possibilities, and the things to do is that we have to set an absolute value for that, and we have to calculate the interference between the 2 processes, okay? Obviously, if you sum these 2, you will be off the data, but this is because there is going to be some interference, and also this is going to be a slightly minor, slightly lower, okay? And well, that's it, no? So there is a lot of things to do, and so far, the calculation I have shown you, it's for QRPA, but what we want is to invite, and we have collaborators already on almost every nuclear strata model in the market. So we have people working with us in IBM, people on share model. We are working with the share model to calculate precisely what I showed you in QRPA. So at the end, we will have the full reaction mechanisms with all the nuclear strata models in the market. We have to combine the transfer that I told you, sum all the process coherently, and then compare with experimental data. No? So far, we have a lot of data already on cadmium, on tellurium, but now the lab is shut down, and it's going to start very soon providing the new data after the break. And to cover a little bit the rest of possibilities, this is not the only one, and we have been discussing also a little bit on the possibility of having double gamma decay from the diagonal isovalent state. That's double isobaric analog state, which, because this 0 plus is in the final nuclei, but is equivalent to the initial nuclei of the double beta decay. So this is also comparable to what you want to obtain, but on the electromagnetic side, okay? And also double gamma Taylor resonances can can be discussed that there is a lot of a certain correlation between that and the neutrino matrix element. Okay? Well, let me switch a little bit to the second discussion, which is the B of E1 on halo nuclei. Okay? B of E1 is the dipole electric probability of transition in the nucleus. I will show you why this is important. No? And this is a little bit to talk about halo nuclei. Most of you will know, but the interest here, or if you go to the low part, to the low mass part of the Segre chart, is the place where we have been able already to find the drip line, okay? And close to the drip line, you have nucleons that are so barely bound that its wave function spreads all over long distances far away from the rest of the nucleus that is usually called core, okay? So this spread turns out into a low density distribution that make this halo that gave name to the nucleus, no? And then you have some very different physics from these guys. And the effort is right now that the new facilities are covering the gap towards the drip line at higher and higher masses. And the complications is that then here usually what you say is that this guy is so weakly bound that everything that happens has to do with this guy, and it's very difficult to excite this guy. For example, here, the neutron is bound by half an MeV. Exciting the core, that is beryllium 10, is 3 MeV, okay? This situation here is not going to happen because this guy is going to be a little bit more, so the core is going to be also exotic, it's going to be excited maybe by 1 MeV. This is not, no? So this is some of the effort that we've been doing, no? So usually, what you do here is that if this guy is inert, you can use here a very simple structure model, two-body model, but then you can put all your effort in your reaction mechanism, and you can have your reaction under control. There is always a balance here, because we cannot put the complexity on nuclear structure and nuclear reaction. And so what you usually do is you send to something heavy, and then this neutron, as I told you, is very weakly bound, so it's going to go out, and you have breakup reaction. Okay? And this breakup reaction is basically a dipole excitation because you move the neutron and all the charge is here. So you are moving the charge by recoil, and this is like a dipole. So a signature of a halo nuclei is the fingerprint is the probability of dipole excitation. Actually, the energy distribution, because this is going to be to a continuum, and this neutron can go to any possible final energy. Okay? And beryllium 11, I'm discussing about beryllium 11 because it's our benchmark of halo nuclei. So the B of E1 of beryllium 11 is the signature of your benchmark. But we have a problem with the signature of our benchmark. We have two different sets of data that they are simply incompatible. And this was a pain on the neck because this is the best halo nuclei, the one that you know the best. And then the thing that you should know for sure is not so clear, okay? So what is going on? So this data is not real data. It's something that you extract. What you really measure is the cross-section, okay? You measure the cross-section, and you apply, or you assume that you can apply the equivalent photon method. You assume that your reaction where you measure this cross-section is very simple. It's only a first-order Coulomb excitation. You have to avoid nuclear to do anything. It's hard, but you can always find a kinematic situation in which this is 99% happening. Okay, let's give it there. But this is a source of mistakes also. And so the thing is, can we do it better? So I mean, we need to start the B of E1, and we need to be sure which one is the right one. Okay, and then this is the original data for the two experiments. I didn't say that we have an experiment from Riken and another from GSI, and the lines are theoretical calculations. And the theoretical calculations with exactly the same structure model, okay? So here there is something that is not going on. So you have the same structure giving the same cross-section, but then if you go back, you get different B of E1. What is going on? The thing that is going on is that I use my best reaction framework in the market for this. So this has not been done in equivalent photon method. This has been done in XIV that I will not tell what it is, but basically the message here is that now with this, I'm taking into account Coulomb, I'm taking into account nuclear, I'm taking into account the interference between the two, I'm taking into account also the core excitation that I told you, so I can see what's happening. Why were we failing? Why are we failing? I know we're failing because there are different sources of deviation between these two. The one is only the convolution, the experimental resolution that is very different, but also sometimes it's the nuclear contribution, sometimes it's the, in here, for example, there is a strong nuclear interference that is taking the cross-section down, and then so you are not good at taking your B of E1. So this is the thing, no? But the thing is, okay, I know what is happening. I need a complex reaction mechanism. Can I still have one-to-one relation to my nuclear structure model? Can I get some idea of what is the B of E1, no? And this is what we've been working out. And the thing is trying to see that whether this is a linear thing, okay? So the B of E1 is the square root of this matrix, of this operator. So the thing is, okay, I have my model, which is not bad enough, it's not too bad. Can I change my model for each data point a little bit, so delta is going to be small, okay? So that I have, this is my original, this is going to be my seed, if you think of something like Monte Carlo, no? And then I have a model value of m, which to the square means that your B of E1 is approximately 1 plus 2 delta, okay? And the thing is, now, this is not going to be 1 plus 2 delta in the cross-section, because the cross-section is hard. But can it still be linear? Can be still a delta linear relationship. So if I change delta 0.1, this is going to be a linear change in the cross-section, because if this is so, I can get delta out of here, okay? I can calculate sigma prime just by putting the new B of E1 and running again the calculation, okay? And then I have the sigma prime, the sigma that I get and the original one, so I can get the delta. Which delta? The delta that provides me the cross-section, not the one I want, the one that is experimentally measured, okay? And so it's this factor, right? So if I put this factor in here, I got from my original prediction, the experimental value. That's the B of E1 that is going to produce me the experimental cross-section. This is the one I want, no? But I have to check whether it's linear, the relationship, okay? This is a little bit dizzy, but there is basically a panel for each data point and for each experiment, okay? And I put the cross-section as a function of the B of E1 that I'm putting in my reaction, okay? Each point is a calculation changing delta by 0.1, okay? So if the relation is linear, these should be straight lines. And you see that all of them are straight lines with different slopes. And the red and the black are basically two different seeds. So I choose two different starting points, basically. And then if you look at this, and you see the crossing, and you put here the experimental value with the error, so you will have here in the crossing the value of B of E1 that you really need, okay? And you also have the equivalent photon method, which was the previous one, no? And you see that there is a significant deviation from the previous one, okay? And you can also see that the two different seeds provide something similar. So this is working. It's not depending on the model that you're starting with, okay? And that's it. This is the original situation, and this is the final one, okay? After putting all the ingredients, you get something where all the data sets are basically within the error bars, okay? So this is what the this is somehow how the situation. No? So you can see here it go from 0.6 to 0.8, and there is no longer 0.6 in there. Okay? And the thing is that we have overcome precisely also the experimental resolution, because this is the thing that you put on your theory. There is a certain effect of the experimental resolution, because if it's too bad, it's going to be something flat. But the experimentalists can do very well, and they can provide something that it's, with a small experimental resolution, you can do something very, very, very good here. Okay? That's it, no? And this is the last one. And so I'm again changing the topic. We are going to discuss now knockout reactions. Okay, what do we do in knockout reactions? Now we go to slightly higher energies. Okay, so we send our projectile, that is the nucleus that I want to look at, times a target, and the energy is so high. So basically this, you are going to get out a neutron from there, and you are going to measure the core. You can get out a neutron or a proton, okay? And this you don't measure, so this can be in here, which is the stripping, or it can be getting out, which is usually called diffraction. And basically the cross-section that you measure is proportional to the spectroscopic factor. So it's telling you basically how much of your projectile looks like a neutron or a proton in a certain level, which can be a weakly bound level, it can be a bound, an S1/2, P1/2, whatever, and that's why you do these reactions. Huh? But this is the situation. If you put your best nuclear structure model, you calculate the cross-section without the spectroscopic factor, and now you take the cross-section experimental and you divide it by your prediction, there is some places where you do very good, some places where you do very wrong. But the thing here is that there is a systematic here, okay? So they follow in line with this. And this is the difference between if you remove a neutron, between the neutron separation energy and the proton separation energy. If you do with the proton, the other way around. What do you want? What you want is that this delta S is negative. Basically, you have something that is, you are removing the weakly bound guy, okay? If you are removing a neutron here, it's because the neutron is weakly bound. And if you remove a proton, it's because the proton is weakly bound. And it's working, there it's working. But if you want to remove the very bound species, you are failing, okay? So it has to do something, there should be some physics regarding this. There has been a long discussions here whether this is a problem from the nuclear structure side, is the problem from the nuclear reaction side. Well, what we know is what we can improve from the nuclear reaction side. And some physics that we were forgetting here is that when you remove a neutron that is very strongly bound, okay, your core is going to finish in a very excited place. It's going to be with a lot of energy. There are going to be a lot of nucleons that wants to cover the hole that you did. And that means that there is a lot of probability that the core doesn't survive that. So the cores get out a little bit, okay, and within in a very small time, it decays. It maybe decays through alpha emission, triton, protons, neutron, whatever is, okay, I have now this hole and I have to get out to a more stable situation. Maybe my more stable situation is to send two alphas or whatever, okay? So this means that you are going to measure less cross-section. And then, so this is going to be small, so the ratio is going to be larger. And here it's not going to change too much. This is what you get, okay? We couldn't, or they couldn't do it for all these nuclei. They select these 6 cases. Red is what you have before. I try to have the same scale so you can compare, okay? You have also the slope that you have in there. And now the green and the blue triangles are including this new physics there, no? Not new physics, but something you were not including before. No? And you see here is the big change, and here remain more or less equal. Okay? And so the slope is very flat now. It's very flat now we compare. There is still something else, and there should be something less, because there is also some people in the nuclear starter side saying that we have to include a little bit more of short-range correlations. No? So this is also undergoing. No? Let me finish with the promise perspective. Okay, all the cases. All the cases I've been talking about are related to having a complex reaction mechanism and trying to improve your structure model. But I told you that we have a certain balance. We cannot put all the complexity there. In red is where you put all your best, okay? So if you want your best in complex reaction, you have to put approximate few body models, no? Some few body models you cannot put in here. They are in here actually, okay? Because they are very precise. And so, but if you start with something like the best you can do in nuclear structure, there are a lot of people doing that, no? So they do their best ab initio or very complex many body, and they try to get a reaction observables from there as well. But the problem is that then you cannot go here, okay? You cannot take into account all the possible processes, because then your computer explodes. But then they are increasing this, so they are. I have all the complexity, and I try to go up from here, or I have everything here, and I try to go up from there. No? And this is nice because we are doomed to converge, but we are also thrilled to converge. Okay, so there is a lot of cooperation in here. And hopefully we can do everything in a not so far time soon. And so this is somehow what we are doing, but there is something else missing, because the requirement from our experimental colleagues is do you have an idea of your errors? And in here usually you can have, for example, a leading order next to leading order. Okay, you have a certain hierarchy, and then you can give some error estimation. But from this side, we don't have that. We don't have that. But there are some people that is taking care of this, and they do it basically with Bayesian methods. And I'm not going to enter in how it's done, but the problem is that you need to run your calculation a lot of times. So you need a lot of time, a lot of computer consuming, okay? And so you are restricted to simple reaction mechanism for now. Okay. Again, also this is something that we are trying to improve. No. So this is the two things. No. So we are hopefully gaining the desired accuracy, and also hopefully getting estimations on our errors, depending on also on the reaction mechanism. So thank you.
Thank you, José Antonio, for this nice talk. And now we have a few minutes before the coffee break for questions.
Very nice talk, José Antonio. When discussing the knockout reactions, at the end you have pointed out something very interesting, no? Which is the role of correlations beyond the mean field. My question is, I mean, we know those correlations are there. They have observed at GLab. We are trying to measure also. But how do you think these correlations may affect also your calculations or the reactions at lower energies? No? For example, when you're calculating double charge exchange reactions, how these correlations affect both the reaction mechanism and your nuclear structure model?
That's a point. Okay, so you can so at the first step they are a little bit decoupled, and you can somehow get all the information from there, even from the experimental data. You can fine-tune your spectroscopic factors so that in this, so in here we can repeat this calculation considering such a process, no? And we expect this to be the major contribution, but maybe the point here is also what is going on along the reaction, no? So this is somehow we say, okay, from a static perspective, this is the nucleus when enters into the reaction, and that's it, no? And you put the correlations there, no? This is something we can do right now. I think we can do it soon, no? And the other question is requires a lot of development, because then if you really want to be able to break this correlation or to modify this correlation along the reaction is a different story, no? Whereas, but if you think about it, it should be a smaller thing, no? But it's something to take care once you solve all the other stuff, no? And also in here, and also in the double charge chain. Well, if I arrive. It's not okay, because it's also some. It's also a strong discussion on two sides. First, on whether this is the key for all the nuclear structures to converge. But other problem is that you are going to explore this correlation, short range or whether long range, depending on the available momentum in your system, no? And this is coming to how similar or how different is your experimental this compared to the other one, no? And this is also an interesting discussion. But somehow, in certain energy and angle regimes, you have a similar energy or similar momentum put it in place. So in principle, you should be more or less sensible or as sensible as the neutrino-less matrix element.
Okay, I have been warned by the organizers that we are, out of time. So I think that we have to finish by thanking again all the speakers of this morning session. And I don't know if there is some advertising or something. Nothing. Okay, we will convene at 11:15.